Hi everyone, I'm Bryce Meredig, co-founder and chief science officer of Citrine Informatics. I'm excited to be able to participate in this virtual event with all of you, and today I'll be sharing our perspective at Citrine on FAIR data and machine learning for material science. I want to start with a brief introduction to the company for those who aren't familiar with us. We're based in the San Francisco Bay Area. We're a software company, and our business consists of selling a materials informatics platform to large materials and chemicals companies. We were proud this year to be named to the CB Insights AI 100 list, which is meant to be 100 of the top private companies in AI. And you can see there we were one of only 4 companies identified in the manufacturing category, which of course is our specialty. We focus specifically on material science and chemistry. To give you a sense of the kinds of companies we work with, many of them, we can't disclose their names publicly, of course, but a few have announced their use of our platform and their partnership with us. So I've shown those there on the slide. And I want to highlight 2 that are based in Germany in particular, Lanxess and BASF, of course. But you can see from those companies that we've shown that Citrine's applications span many different areas of materials, many different classes of materials. We don't just specialize in one particular area. It's quite broad. So to give you a little more information on what we mean by a materials informatics platform, here's one way to think about it. We envision a fundamentally iterative materials development loop or materials innovation loop where we're synthesizing samples of materials, we're characterizing them, measuring their properties, we're performing data analysis, and in our view, all this information ought to be feeding into a machine learning based optimization loop that is then in turn suggesting what are the next candidates to synthesize, how should we characterize them. We also think it's critical that these machine learning models are as physics informed as possible. And one way to do that, that I imagine many of you in the audience are familiar with, is by using physics-based simulations to generate training data for machine learning. So you can see that there's a feedback loop as well between physics-based simulations and the ML optimizer. And our view is that this kind of framework can fundamentally change and accelerate the timescale of materials innovation. So with that background in mind, I'd like to talk about what we see as some current needs in materials machine learning and specifically some high impact areas for new research. These are areas that, in our view, where new developments will have sort of outsized impact in the field. One, of course, is experimental validation. I think what we've seen over the past few years is that simply training a machine learning model has become easier and easier with open source software packages. But what's really needed at this point is more studies where the results are experimentally validated or validated via physics-based simulation, some kind of ground truth. So this is something, of course, we focus on a great deal at Citrine. There's also a great deal of work to be done in materials and chemical-specific machine learning method development. We should always be asking ourselves the question, how do the problems in our field fundamentally differ from the problems that people in the machine learning research world are focused on? We found a number of these differences over the years, and those have motivated a lot of the method development work that we do. Of course, because machine learning is very data hungry, it's important to be able to generate new training data as quickly as possible, both experimentally and with simulations. And of course, I know many people involved in this conference have been involved in the high throughput DFT community over the years. We also are interested in machine learning that strengthens the ability of human scientists. This is the idea that machine learning or AI can be a very potent co-pilot because the abilities of machine learning and the abilities of the human expert are very complementary. So we think that this is a useful frame of mind to have when doing method development. And lastly, again, we think it's critical to be integrating known physics and physics-based simulations into machine learning for material science. So this is kind of a way of organizing the research that's going on right now in materials and machine learning and where we think it can have the most impact. For the remainder of my talk, I'm going to focus on 2 of these in particular, material-specific method development and integrating physics into machine learning. So let's first turn to material-specific machine learning methods. To introduce the particular example that I'll be walking through today, a lot of the publications in the materials informatics literature address very clearly the question of model quality. How accurate is our machine learning model? This can be quantified with metrics such as R squared or root mean squared error. Another common consideration is training data quality and quantity. Do we have enough training data? Is it plagued by noise? Can we rely on it? These issues are well addressed, but one question that's received less attention in our view is design space quality. If materials discovery is commonly compared to finding a needle in a haystack, The design space quality question is the question of, are we looking in the right haystack? Does this haystack contain any needles at all, or is it hopeless? So at Citrine, we've done a good deal of work to investigate this question with the goal of developing predictive metrics that could perhaps help us assess the goodness of a haystack before we actually start doing a project. So I'll walk you through some of that work right now. This figure you see on the slide is a common way we visualize the results of design space quality benchmarking. So you can see here the x-axis is the fraction of improved candidates in the design space. We start with an initial small training set from a larger database of materials properties. And then we ask the question, how many of the held out materials that aren't in our initial training set are better than the best material in the training set? So that's the x-axis is essentially a metric of a measure of how good the haystack is, how many needles it contains. Then the y-axis here is the number of iterations of that sort of sequential learning or active learning loop that we have to go through before we find our first improved candidate. Finally, the black curve that you see on the plot is the benchmark of random search. So you can see, for example, at the where the x point is 0.1, or where 10% of our design space candidates are improved relative to our training data, you can see that it takes on average 10 random trials before we find one of those improved candidates. So that kind of makes sense. So now what I'm going to do is show you the results of many different simulated sequential learning runs, where we've, again, taken a large materials database, held out most of it, trained on a small fraction, and then asked machine learning to suggest candidates to explore in that list. And you can see we rely on a number of well-known databases to do this benchmarking. For example, these are results from Materials Project. You could imagine asking machine learning to maximize or minimize the formation energy of a compound. That doesn't make a lot of physical sense. It's not a real-world application, but it is a perfectly valid optimization problem that we could benchmark. We can do the same thing with band gap, with total magnetization, and then turning to the organic chemistry world, using the Harvard Clean Energy Project dataset from Alana Spurguzic's lab. You can imagine maximizing or minimizing the HOMO energy of these photovoltaic molecules, or the power conversion efficiency. And you can see I've all those multicolored points, those benchmark results I've put on the plot. And you can see that in the vast majority of cases, the machine learning guided sequential learning runs do better than random search, i.e. they fall below the black curve, but which is of course reassuring. But one takeaway I want to highlight from this plot is, as you go to the left of the x-axis, i.e. as the materials discovery problem becomes harder and harder and there are fewer improved candidates to find at all, the number of iterations to improvement blows up, and that's true regardless of whether you're randomly searching or whether you're using machine learning. So that's further motivation why being able to say something a priori about the quality of a design space is so important. So we've developed, at Citrine, we've developed metrics to attempt to shed some light on this question. One such metric that we've developed is the cumulative maximum likelihood of improvement score. So before I talk about the cumulative part, I'll describe what we mean by maximum likelihood of improvement. At Citrine, whenever we train a machine learning model of a material's property, it's always probabilistic. So we generate probability distributions of possible values of the property for a given materials candidate. That's shown in the cartoon on the right. And then you can imagine examining as a threshold, the current best known value of that materials property or figure of merit, and then integrating the value of that probability, the area under that probability curve above or below that current best known value. So that's the red shaded region. This is what we would call the maximum likelihood of improvement. Now that becomes cumulative when, instead of considering one materials candidate at a time, we consider, for example, the top n candidates. And commonly we might, n is an adjustable parameter, but we might choose, for example, n to be 10. And then we're asking the question, what are the chances that at least one out of the top 10 machine learning recommended candidates are in fact improved materials? And that's of course very motivated, again, when we're doing real world materials development projects. So let's see how CMLI does across a wide variety of materials benchmarks. So I've used some of the same benchmarks as before, as well as some new ones involving experimental data as well, just so you can see that this sort of metric works across many different properties and materials and classes of interest. And what we specifically do is we think about thresholding the CMLI score and saying that any design spaces that score below that threshold, and that's again, of course, a tunable parameter, would count as low quality design spaces. So you can see that in this case, CMLI thresholded at a value of 0.8 does a good job of filtering out a lot of low quality design spaces. Those are the benchmark results in the lower left corner of the plot. Of course, we've developed other metrics as well that attempt to highlight high-quality design spaces, and then you can imagine ensembling these metrics to develop a classifier for projects that are promising and projects that are less promising. But this is, again, the kind of work we do, given that our customers are all interested in accelerating materials development, and they can't pursue all possible projects. So we like to be able to help them prioritize possible materials development avenues. Now, given the theme of this conference, I wanted to highlight how important FAIR data has been throughout Citrine's history. And in the example I just showed, FAIR data sets enable us to perform that the benchmarking for the ICMLI score. So we rely on data sets published by researchers in all fields of material science and chemistry to benchmark our methods. I think this is incredibly important because we want to make sure that our methods generalize well and that we're not overfitting them to a small number of materials problems or data sets. And I think this is a challenge, for example, that is becoming better understood in the machine learning research community, where the number of different data sets that are used to validate new methods is actually not that large. I also want to point out, given the attendees at this conference, that in my view, the high throughput DFT community has really led the way in FAIR data for material science and chemistry in many respects, and I certainly anticipate that will continue. And then for our part at Citrine, we try to give back to the community by releasing data in JSON format, so it's machine readable. This is our physical information file, or PIF, which is an open standard. We have on our platform, citrination.com, millions of records, both experimental and computational, that can be used to train machine learning models, and you can access them programmatically. So now I want to turn to the second part of the talk and discuss how we think about integrating known physics and physics-based simulations with machine learning for materials. And the way this manifests typically is by using machine learning as multiscale glue. What do I mean by that? Well, let's talk about the opposite end of the spectrum. I would claim that robust, easy-to-use open source tools like sklearn and TensorFlow, other libraries, have completely solved the sort of one data set, one model machine learning use case. If you have a CSV or Excel file with a bunch of materials properties or a bunch of marketing data, it doesn't really matter. You can use these existing libraries and a large number of different algorithms to train really sort of good regressors or predictors on these data sets. But in material science, very often we're interested in combining many sources of knowledge that involve different length and timescales. Often these data sets are fairly small, maybe hundreds of records or thousands. We don't have one massive database, and we want to integrate all this information together into the same predictive framework. This is what we focus on building at Citrine, and we use probabilistic graphical modeling framework to do this. So here's just a cartoon of what we mean by using machine learning as multi-scale glue. You can see here in this case, we're training a machine learning model to predict fatigue strength of alloys. This is just a schematic representation. But you can imagine that we have many sources of data to bring to bear on this problem. So we could run simulations on the microstructure of the material. We could run CalFat and DFT, other physics-based simulations, and feed all of that information into our machine learning model that's attempting to estimate the fatigue strength. We also have access to a large variety of different experimental data sets that might correlate in some way with fatigue strength. Let's imagine we have a high throughput database of hardness measurements. There might not be an analytical expression that tells us how hardness relates to fatigue strength, but if there's some correlation we could exploit, we'd want to do that. So you can see there are many different machine learning models in this schematic that are all feeding information in essentially as descriptors to a machine learning model that's attempting to regress fatigue strength. So this kind of framework is how we at Citrine think about combining these multi-scale data sets with machine learning. Under the hood, one of the ways in which this is commonly done is through transfer learning. This is a methodology that's beneficial when you have some data sources that are information rich and others that are information poor, and you want to see if there's an opportunity to take signal from the information rich data sets and transfer that information to the data poor prediction problem. So to give you an example of this, imagine we want to predict the experimental band gap of compounds. The sort of simplest approach would be to take an experimental data set of maybe 1,000 or 2,000 records and simply train a machine learning model given the chemical formula to predict the experimental band gap. And the figure on the right shows you the learning curve when you do this. So as a function of training data, volume, what's our root mean squared error? But of course we would recognize, hey, we have more data available to us than just the experimental data set. We also have, as many people at this conference know, access to very large data sets of DFT calculated band gaps. And while sort of a vanilla GGA band gap might not agree well with an experimental band gap on an absolute basis, we know that there's a strong correlation because the errors are systematic. So we can exploit that by training a machine learning model. And using the the machine learning model trained on the DFT data as an input to the experimental model. So when we do that and perform this transfer learning, you can see that the error goes down. That's satisfying. So we go from the orange curve to the black curve. But what I call your attention to is for a given error value, the difference in the experimental data set size. It's around 50 examples. And in principle, what that means is for a given level of error that we're looking for, we can save about 50 experiments if we're taking advantage of the DFT data that we have available to us. And that's, of course, extremely compelling, I would claim, across any materials discovery use cases, but certainly in industry where we're interested in moving as fast as possible and not repeating experiments if not necessary. So we can go even further. This is another example that we presented at a conference where it turns out there's what we want to do here is think about combining sort of the big three sources of information about how materials behave: experimental data, computational data, and analytical theory or empirical theory. And in this case, there was an old paper several decades ago that published an analytical expression for the elastic modulus of ceramics. One way of applying machine learning then is to estimate the material-specific parameters that enter into that elastic modulus expression. But we can actually go further than that. We can say, well, we have access to DFT-derived data sets of mechanical properties. We can use train machine learning models on those DFT data sets and use those models as further input to this model that's predicting the parameters for the empirical expression. And what the table on the right shows is that as you add more information, as you add the atomistic data, as you add the empirical model, your R-squared score continually goes up as you add this additional signal. And that's, of course, very satisfying. Now, the difference isn't night and day, but it's significant enough that it's motivated. And at Citrine, we focus on trying to make this as easy as possible across many different materials problems. So with that, I'd like to summarize. Citrine has a unique perspective on FAIR in general as a software company, but as a company that focuses on materials informatics specifically. So data is always a critical need for us and our users. I showed you an example of how our method development benefits from FAIR data, and we do our best to give back to the community by making a great deal of data machine readable and openly accessible on the Citrination platform. And lastly, I hope I was able to show you that, at least in our view, machine learning is most useful when we're combining many different models trained on different data sets at different length scales and bringing those together with domain knowledge to make our models as predictive and sort of physically motivated as possible. So with that, thank you very much for your attention. I'll leave my contact information up here, and I'm happy to answer questions.